So we are on air, I guess. We switch to English because we do have some non-German speaking people here. It's my pleasure to introduce to you Tom Pock as our final guest speaker for this semester. We have summer break after Tom left, in terms of invited talks at least. So this is our ICG lab series. As every month we have one distinguished guest speaker, usually remote, but we are very happy to have Tom here in person today, so you can talk to him and watch with him soccer tonight. We hope that Austria makes it, but we are unsure. Let's see. So Tom is a professor at TU Graz. He recently became a professor, a full professor there on mobile computer vision. He was an assistant professor there before at the Institute for Computer Graphics and Computer Vision. He did his master and PhD also in Graz. And he is interested in basically developing mathematical models and algorithms for computer vision and image processing, and in the context of mobile scenarios. As you see in the slides, he's very successful in terms of funding acquisition. He received an ERC starting grant, I guess, and the start award of the FWF, which is the National Science Foundation here in Austria. And he's doing very, very high level and also exciting research. And we invited him because at the moment he is interested in machine learning and computer vision, and this is also of interest for some of our people. We hope that we can learn something from your talk, which is entitled Learning Better Models for Computer Vision.
Thank you very much. So, hello everybody, welcome to my presentation. First, I would like to thank Oliver and Mark for inviting me and giving me the opportunity to talk to you today. And as Oliver said, today I would like to talk about our recent activities to learn better models for a variety of image processing or imaging problems. And basically this work started with the first paper with Karl Kunisch, who's at the Karl Franzen University in Graz, and then I continued with my two PhD students, Yunjin Chen, who already finished his PhD last year, and with Kerstin Hamanik. Okay, so in this talk we consider different applications in image processing. The most easiest one you can think of is image denoising. So today I've already seen an interesting application with flexible imaging devices where you also need some sort of image denoising. So this is not only an academic problem, but there are real-world problems where you can apply image denoising algorithms. Second one is image deconvolution. Here there's a specific problem where the point spread function, so this little thing here in the top left corner, is known, and the idea is you would like to reconstruct a sharp image from the blurry image. Next application could be image inpainting. Image inpainting is a problem where part of the image information is lost. So as you can see here on the left-hand side, so the black information means, or the black lines means that the image information is lost here, and the task is to reconstruct an image that is, of course, equivalent to the given information, but looks as natural as possible. So you would like to hallucinate or invent new information in missing regions. Another very practical and almost daily problem is JPEG deblocking. So everyone knows JPEG images, where you have these characteristic blocking artifacts, which come from a certain compression process on the coefficients of the discrete cosine transform. And the idea is, can we find an image that has the same discretized cosine transform, but looks more natural, for example. It's kind of an image denoising process, but with different constraints. And finally, and I will come back to this application in the end of the talk, which is our most recent application, that is magnetic resonance imaging reconstruction. So an MRI scanner acquires information in the Fourier domain, the so-called K-space. And when you do subsampling, compressed sensing in that space, you introduce a lot of artifacts because the sampling theorem is not valid anymore. And the idea is, can we reconstruct from the compressed information a better image? Okay, so I'm dealing with optimization approaches for computer vision, and one might ask, why is this a good idea? And I think sometimes it's good to listen to old masters. And here you see Leonhard Euler. And in 1744, he made the following statement. And he said that nothing in the world takes place without optimization. And there is no doubt that all aspects of the world that have a rational basis can be explained by optimization methods. And so for me, this is good enough to say, okay, let's try to solve computer vision and image processing with optimization approaches. So usually when you look at optimization approaches to image processing problems, computer vision problems, or inverse problems, you find a particular structure that turned out to be quite successful. You find optimization problems that are given by the sum of two terms. On the left-hand side, you have a so-called regularization term. And on the right-hand side, you have a data term. The data term somehow connects your solution, the denoised image or the MRI reconstruction U, with your input data. The input data could be a noisy image, could be Fourier data, could be any sensor data you have acquired. And the regularization term that puts a prior to your solution. It's a so-called smoothness prior. So if you know, for example, my solution is piecewise constant or piecewise affine, piecewise smooth, or textured or whatever, you could try to look for a suitable regularizer that puts this prior knowledge to your solution and favors, for example, smooth solutions. And the key to the success of this kind of approaches is to model both terms, the regularizer and the data term, such that low energy states reflect the physical properties of your problem. And then when you're able to compute the minimize of the problem, you of course have the best solution to your problem in terms of your model, of course. So big question is, and people tried a lot in the last, I would say 30, 40 years to find better models, to find suitable models for particular image processing problems. And the question is, how can we find good models for the regularization term and the data term? And in this talk today, I'm talking about the machine learning approach to learn better models for the regularizer and also sometimes for the data term. So let us first consider the most simple variational model for image processing, which is for image denoising. In this case, if you assume you have Gaussian noise, it turns out that the least squares data term is an almost optimal approach. So you try to find an image U that is in a least square sense similar to your noisy image F. And it should also have a low regularization term, R of U. And a very popular regularizer that has been, dates back to Rudin, Osher, and Fatemi of 1992 is the so-called total variation. And the total variation is nothing else than opacity in the edges of the image, so nabla, here this sign. This operator here is a gradient operator that computes derivatives, spatial derivatives of an image, so it gives you a notion of edges. And the L1 norm is known to impose sparsity on the solution, so you would like to find an image that has only a few sharp edges and most regions of the image should be flat. And as you can see, this is a very simple regularizer, but I spent my whole PhD on basically on studying this regularizer and tried to apply it to different image processing problems. When it comes down to implementation on a computer, it turns out that this nabla U is nothing else than convolving your image, your 2D image, with a filter kernel that looks like this for the X gradient and the filter kernel that looks like this for the Y gradient. So it just computes finer differences on the discrete lattice. Of course, there are several generalizations have been proposed. Some were based on the notion of infemal convolution. And one of that is the so-called total generalized variation, which I developed jointly with Christian Bredes and Karl Kunisch. And here you see the difference of the total generalized variation to the total variation. So you see if V is 0, they coincide, but it's some kind of nested optimization problem where affine regions in the image can somehow be stored in this additional unknown V, and V itself should be piecewise constant so that piecewise affine regions are well modeled with this combination of these two terms here. So an image is more than 1,000 words. So here you see a short example for image denoising. So here on the left-hand side, you have a noisy input image. By the way, do you know who this is? should know it, it's Charlie Chaplin in early days. In the middle, you see the result of total variation regularization, and you see the typically piecewise constant solution because it has sparsity in the edges. So you see these blocky regions here, for example here, and on the right-hand side, you see the solution with total generalized variation, which is already a better model because it allows for piecewise smooth reconstructions. However, it turns out it's still not good enough for us, so we would like to get much better results, and images are not piecewise constant, they are not piecewise smooth, they are much more complicated. You have textured regions, for example, when you look back here, there's a lot of texture here, and the hair has a lot of texture, fine structures, and this cannot simply be modeled with total variation or with total generalized variation. And therefore, when this story starts, it was in 2012, me and Karl Kunisch were thinking of how can we somehow generalize the model and try to find or to learn a better model. And the first simple idea was, okay, don't only take one L1 norm like in the TV, take a sum of L1 norms for a variety of different linear operators. So one linear operators could be the gradient, but it could also be second order derivatives, it could be a DCT transform, whatever you would like to have. So we were thinking of this model, which has a sum from 1 to q of L1 terms of given linear operators. And our idea was to try to use machine learning to compute the different weightings of the terms. So for example, if it turns out one of these theta k parameters is 0, it means this linear operator is not used, so it's not suitable. And different weights of the parameters will turn out to, to emphasize different operators here. This is from an optimization point of view, it's an easy problem because it's convex. You have the sum of L1 norms and the squared 2 norm. It's a convex problem. It's non-smooth because the L1 norm is non-differentiable, but since the data term is strongly convex, it admits a unique solution, and the optimality condition can be written like this. So here you see actually a nice structure. You see on the right-hand side, here you have the noisy image. Here is the denoised image, and obviously the noise should be modeled with this term here. And this is nothing as the transpose linear operators times a dual variable lambda k, and lambda k is restricted to lie pointwise between -1 and 1. So this oscillatory part should be somehow modeled with these linear operators. So what are some linear operators that we used in our first model? So you see as before, first derivatives, which leads to the total variation. Then here's a combination of first and second order derivatives. So you see these typically stencils that are used to approximate second order derivatives in image processing. You could also take the functions of a discrete cosine transform, a 2D discrete cosine transform. So these are the basis functions, or you see here the basis function of a 5 times 5 discrete cosine transform. These are all these different operators we tried. So how can we choose the weights for different operators? That's of course a question. And our approach was to use empirical risk minimization. So the idea was we set up a loss function that measures the loss or the error between the reconstructed solution and the ground truth solution. So this is this mean squared error here. So U is the reconstructed solution from the model, and G is a given ground truth image, which is, in case of image noising, very easy. You take clean images, you add noise, so you have your noisy images and the ground truth very easily. And this U of theta is the minimizer of your model. And as you can see here, this is a nested optimization problem. So you minimize the loss function, subject to that U of theta is the minimizer of your model, and this is called a bilevel optimization problem. In the machine learning, this type of approaches is called empirical risk minimization. So the interpretation of these bilevel optimization approaches, we try to find our parameters theta. These are actually the unknowns, such that the minimizers of the models for all different input images we can test minimize the loss function. And in our first work, we have developed specialized semi-smooth Newton algorithms that are superlinearly convergent and worked very well for this problem. The only problem is that Newton requires some smoothness because you also need to compute the Hessian matrix. So we needed to replace the L1 norm with a smooth approximation, but in practice this worked quite well. Okay, here are the results for our first model. So I call it L1 learning, and in order to learn these parameters, we set up a training database consisting of smooth images. So we just put together 64 times 64 patches to have to maximize the variety of different images, and we just added Gaussian noise to get the noisy images. And it turned out that the more different linear operators you have, so here you have just first order derivatives, here you have DCT5, much more linear operators, the value of the loss function decreases, which means that the reconstruction is better. And this is consistent for different values of the noise. So here's a sigma 15 for the noise, and here's a sigma 50, much more noise in it. However, what turned out is we even tried more DCT7, DCT9, combining everything together. There's a certain limit where you cannot go beyond. There was a hard limit, and then we were trying to find out what is the problem, and the real limitation in our model is the convexity of the regularizer. So it turned out a convex regularizer is not a good enough model for image processing. So here are some results. So here you see the clean image, the noisy image, and here are the results for the different linear operators, and here are some subviews where you can see the differences. To be honest, you don't see much difference because, as we will see later, the real problem with this approach is the convexity of the model. So therefore, we were looking for a different model, and the different model is much more powerful. First of all, the regularizer is now a sum of more free potential function. Before rho was just the L1 norm, but now this function rho L is derived from the statistics of natural images. When you, for example, take arbitrary zero mean filters applied to natural images and you draw the statistics from the responses, you typically see this type of curves. So these are the so-called heavy-tail distributions. So it means most of the regions have no response because they are flat, and there are only a few very sharp edges. So this kind of statistics you see in images, and you see that this is very different from an L1 norm. So L1 norm is like a V here, and this is a more concave type of function that you can derive from the statistics of natural images. But this function can be very well modeled with the student t distribution. So when you take logarithm of 1 plus some parameter times t squared, you can, and you see that these functions provide a very good fit to the true statistics of natural images. So this model now has these non-convex functions here instead of the absolute functions, and additionally, the linear operators are now not restricted to given ones. We also try to learn the linear operators. So we now try to learn filter kernels, completely the filter kernels that perform best for image denoising. While the first model had around between 5 and 20 parameters, now this model has several thousands of parameters. For example, if you have one filter kernel, 9 times 9 is 80 parameters. Let's say we have 80 filter kernels, 80 times 80, and a few additional parameters, alpha L and beta L for the potential function. So you see you easily get a few thousand different parameters. The problem of this model here, but it turned out not to be that big problem, it's a non-convex problem, so we cannot hope to compute the globally optimal solution of the model. We can only hope for getting a stationary point, for example, a local minimum. We can, in order to learn the filter kernels and their potential functions, or at least the parameters of the potential functions, we again use a bilevel optimization approach. Now it's just that the lower level problem has been replaced with this more general, with this more powerful model. Since we now have several thousands of parameters, the Newton algorithm is no longer applicable. It turns out that it doesn't work because it takes too much time to compute the Hessian matrix, for example. But however, since the lower level problem is smooth, so these row functions are infinitely often differentiable, we can make use of implicit differentiation in order to compute gradients of these reconstructed images with respect to the parameters. And here's the formula for computing the gradients. And what we see here is we first need to solve the lower level problems optimally. So we need to minimize it for our given parameters. Then we need to compute the Hessian matrix, invert the Hessian matrix, and also multiply it with this mixed derivative here. But this is simply implicit differentiation. And with this formula, you can compute the gradients of the loss function with respect to the parameters, and then you can use an off-the-shelf optimizer. Here we use the LBFGS quasi-Newton method, for example. It just takes the gradient and the function value of the loss function as input, and this works quite well. Okay, so in a paper together with Eugene and René, we set up different problems, and one of the problems, in one of the problems, we learned 80 filters of size 9 × 9, and plus the function parameters were in total 6,480 parameters. And we used a database of 200 training images. And this took 2 weeks. And 2 weeks later, Eugene came and showed me this here. So these are the learned filter kernels. And here are the corresponding learned potential functions. And it was very funny to see they are ordered by their importance. The first one you see is exactly the total variation, right? So it's exactly the finite differences that was in our very first simple model. So this seems to be really important because it models edges. But you also see anisotropic filters, you see highly oscillatory filters that are used for texture modeling and so on. Also Gabor-like filters. Everything basically you have expected is then seen in the final result. In the potential functions, we see a mixture of more non-convex functions like this here. So if it's concave, then it's a non-convex function, of course. And you also see quadratic functions, you see L1 type functions, and these are basically obtained by different combinations of these two parameters here. So with these two parameters, you can scale your function such that it has a slightly different shape. So we applied it to a database, to a benchmark, in order to compare it with the state of the art. And it turned out now this really works well, and we were able to be on par with the state of the art, or even slightly better for some noise levels. So here you see one of the best approaches for image denoising, for example, BM3D is a well-known, well-engineered approach. And with our learned approach, we were able to outperform, for example, BM3D. So here's one example. This is the clean image, this is the noisy image, and this is the denoised image. And you see it's very successful to denoise homogeneous regions. But also edges are very well preserved, and textured areas like here the bushes, for example, you see that this is very well preserved. And I would not be able to really model this by hand. I think simply there's no chance. You have so many different choices for your terms. You need really machine learning that learns you the best model for these problems. So let us have another look at computing the gradients. So this was still a bottleneck I've already explained before. First, we have to solve the problems in order to get at least a local minimizer. This is this U star. Then we have to compute the Hessian matrix, and we have to invert the Hessian matrix, which boils down to solve a linear system of equations. So this is very time-consuming, and therefore the learning took more than 2 weeks. And another problem is, it turns out that if you don't solve the lower level problem exactly, so that you're still a little bit away from your stationary point, then the gradients you're computing with this formula contain a very big error, because usually the Hessian matrix is ill-conditioned, and then inverting the Hessian matrix really amplifies your error in your solution, and then you're getting wrong gradients, and then also the optimization doesn't work very well. So there's another idea, and this already brings us closer to what our most recent model is. There's a simple idea. You take your favorite solver for your lower level problem. Let's say it's gradient descent. Of course, they're much better, but let's say it's gradient descent, and you unroll the steps of your gradient descent, which looks something like this. You start, for example, with the noisy image as your initial guess, and then you just make a gradient descent. So H is the step size, and this is the derivative of your model. And let's say we do this for t iterations. And then what you can do, instead of using U star as your minimizer, you simply take ut as your final result and write it here in the loss function. And since this is a well-defined sequence of gradient descent steps, you can just use the chain rule or backpropagation, as it is called in deep learning, to compute a gradient exactly from your last iterate with respect to all parameters. So nothing like implicit differentiation is then needed anymore. And it turns out that when you do this, it leads to significantly faster learning. And it was also funny that, for example, if you say, let's take less steps, not 100 or 200, just let's take 20 steps or 5, then it tried to make the best out of 5 or 10 steps. So also the model was adapted such that you get better results only for a few number of steps. And here we really needed to solve it theoretically for an infinite number of iterations in order to get the local minimum. And when we did this, then Yunjin had another idea. He said, okay, now we have these unrolled steps of gradient descent. Why not to allow the algorithm to modify the filter kernels and the potential functions in each step separately? So now it means that we again have this type of gradient descent step, but now we allow that these filter kernels, KT, the functions, which are the derivatives of the potential functions, and maybe also the data term or the regularization parameter changes separately in each iteration. Of course, this increases the number of free parameters by a factor of 10, for example, but you also have more flexibility. And it turns out that this model works really much, much better than the previous model. So as I said before, this first term here is the derivative of our regularization term. So where these phi function is nothing else than the derivatives of the potential function. And the second term is the derivative of a data term. Here it's written in a more general form with a forward operator. The forward operator could, for example, be a blur kernel. In case of denoising, it's just identity. It could be a Radon transform. It could be a Fourier transform or a mask for inpainting. So this defines your type of image processing problem. And yes, this model has much more free parameters. Usually several 100,000 parameters are here now free. So the thing we are still not sure about is how to interpret this model. Basically, we can provide 3 types of different interpretations. First of all, it can be seen as a generalized version of the classical Perona-Malik nonlinear diffusion model. So the Perona-Malik model is as follows. You start with an initial guess, for example, the noisy image, and then your time derivative is defined as the divergence of some diffusion tensor that is based on the gradients of the image times the gradients of u. Here we have replaced the gradient with much more general operators. These functions are also much more general, and actually the divergence is nothing else than the negative transpose of the gradient, and here we just use the transpose of the filter kernels, of course. So this is one possible explanation, because diffusion or PDs are much more general than optimization. So also in Perona-Malik model, this diffusion tensor is allowed to change over time, and it's very hard to find the corresponding energy to that. In some cases you find that energy. The second step interpretation is that in each step, we make exactly one gradient descent step with respect to an energy of this form. This is exactly the energy we have seen before. But now in each step, the energy is allowed to change. So we make one step for this energy, then the parameters change, we make another step for another energy, and so on. So it could adapt to the problem and is allowed to change over time. The third interpretation is a connection to deep learning. If you unroll the loops, you basically see, when I go back, linear operator times u is a convolution. Then the application of phi is a pointwise nonlinearity. And then you convolve again with the transpose filter kernel. And when you write this down, you can see this is exactly a recurrent neural network. So here you see there's the first convolution, nonlinearity, convolution with the transpose kernel, and summing together. And you're adding your derivative of the data term, which can be seen as a reaction force. So it's a sort of specialized convolutional neural network. So learning is more or less straightforward. Now, since you have unrolled your model, it's just application of the chain rule in order to compute the gradient. It's very nasty to do this by hand, but it can be done. And the three parameters basically consist of the nonlinear functions, the filter kernels, and the regularization parameters. Here in this work, we have replaced the student t functions with just two parameters with a much higher parameterized function so that we can reconstruct very different or almost arbitrary smooth functions here. You will see in a minute how they look like. What was really surprising, normally in optimization, you take 100 or 200 steps in order to find a local minimum. But here it turns out that 5 to 20 steps of the low-level problem are enough. So the final model you're learning is also very efficient. So you can say, I only take 5 steps, so give me the best from 5 steps. So it's, per definition, very efficient, usually a few 100 milliseconds on the GPU. So we applied this to the same training database as I have shown before. And here are some results, what we have obtained in our model. So the first image refers to the derivative, and when you integrate this function, you get basically the potential function. And these 4 functions are the 4 most typical functions we find in our model. So you see, this is like a truncated total variation, which has been used before. Then you find something like a negative Mexican hat. You also find truncated concave functions, which is very strange, and also double-well penalties. And the interpretation of, for example, of concave functions is they prefer higher responses of certain filters. So they do some kind of sharpening or contrast enhancement. So this type of functions, they just regularize, they decrease the contrast and they smooth the image. But this type of functions, they also enhance the contrast. So this is the reason why we get better results in the end. And when we look back to very old work, for example, Zhu and Mumford, they use a statistic approach in order to learn functions and filters. Very early approach, they find very, very similar functions here. So it was quite a surprise that we have a completely different approach on empirical risk minimization. We get very similar models in the end. And also in PDEs, for example, there's a notion of so-called forward-backward diffusion, and they use very similar functions to this one here, but they are purely handcrafted, and it's very hard to compare them, of course. So here are some learned linear operators. You again see finite differences, sometimes also non-local. You see elongated anisotropic filters as before. So it's hard to say which filter is necessary, which not. I think the combination of all the filters is important. So now what I show here is exactly the 8 steps the algorithm is doing. So here it's learned for 8 steps in order to denoise this image. So here you see the quality of the reconstruction. This is the peak signal noise ratio, more or less the mean squared error. First step, you see already a lot has been done in the first step. Second step, 4, 5, 6, you see the p-SNR increases consistently. Last step. So basically, in 8 steps, the image is denoised. And when we compare this on the database, it turns out that our model, even with 2 steps, is better than the complete state of the art. So for example, PM3D is 28.56. State of the art algorithm with 2 steps, we already have 28.58. And it's consistent also for, if you have, for example, this is with 5 times 5 kernels. If you have more kernels, 7 times 7, it gives you even better results. So even the model with 5 steps here is better than much more complicated models that has been proposed before. In terms of computational speed, it also turns out it's very efficient on the GPU. For example, let's take 1,000 squared images. PM3D takes 17 seconds. Our GPU implementation takes 0.05 seconds. For the larger model, 0.1 seconds. And one model which is almost as good as ours, the shrinkage fields, for example, they take 40 seconds here. So you see it's quite a huge factor. We are faster here. Okay, last but not least, I would like to show our most recent application of this technology to reconstruction of magnetic resonance images. And this has been recently published at the ICMRM, which is the largest symposium in the field of magnetic resonance imaging. We also received an award, and it's joint work again with Kerstin Hammernick, which is my PhD student, Florian Knoll, and Daniel Soliksen from NYU. Okay, just a few words about MRI reconstruction. So I think most of you know how MRI basically works. So the basic idea is you have a strong magnetic field, so such that all spins of the water molecules are aligned with the field. And then what you do is you put a high frequency pulse to your space, and then the spins of the molecules start to oscillate a little bit. So it's like you have a spin top and you touch it a little bit, then it tries to equilibrate again. And while the hydrogen nuclei are doing this, they emit a detectable radio frequency. And this you can detect with antennas, the so-called coils. And with each signal pulse, basically, you can acquire in the Fourier domain one line here. Okay, this is so-called K-space, and when you put one pulse, this is this characteristic noise you hear when you're lying in MRI, you can get one line here. And due to physical limits, because it takes some time until these spins are back again, back aligned with the field, it takes a certain time to get one slice here. So for example, for a 256 squared slice, it takes about 4 minutes. And time is money, and of course, the scanning producers like Siemens, for example, they are interested in speeding up this process. And one of the basic ideas, first of all, so-called parallel imaging. So if you have the combination of different receiver coils, so it's like different illuminations. So you see it's here it's more sensitive in this area, here it's more sensitive in this area, here, and basically you can acquire different information at the same time, and combining this, of course, reduces the scanning time. And this is also used for so-called accelerated MRI. And accelerated MRI means that you also try to subsample. So you do compressed sensing in your Fourier domain. So instead of taking, for example, like here, every second row, you take only every fourth row, every sixth row, and so forth. But the problem is, of course, if you have subsampled your data, when you try to reconstruct it by just inverting the Fourier transform, you get so-called backfolding artifacts. So here you have not so many artifacts. If you have a factor of 4, you have more artifacts, more, and so on. This happens when you just inverse the Fourier transform, and therefore people were thinking about a least square solution, which is the so-called sense approach due to Bussmann of the old approach of 99. The basic idea is, okay, I have the data from my different coils, which is stored in F. So I have Q coils, and I put all of them together. I have my different sensitivities, which is a pointwise multiplication with the image in the usual image space. And then to each of this information, I apply the Fourier transform, and then I try to find an image U that minimizes the squared error. It's a standard approach. And this is, of course, given by minimizing the squared energy. And since it's linear, it's just a pseudo-inverse you need to compute here, which is very fast. So how does it look like for real-world data? So in the clinical standard, nowadays, what you use is a subsampling factor of 2. And with this approach, you get nice images. This is the quality you usually have. But when you start to subsample more, for example, factor of 4, you start to amplify noise. And if you even subsample more, factor of 6 here, then you have a lot of noise here. And of course, it turns out you need some smoothing, some regularization in order to get better results. And therefore, what people were doing, now we're back again to the total variation, they try to combine the least squares data term we have seen before of sense with a regularizer, and the most simple choice is the total variation, so sparsity in the edges. It turns out, yes, it works, so it can avoid backfolding artifacts and noise. But as before, for natural images, the total variation is too simple to give you good images for MRI reconstruction. So for example, if you regularize not enough, so if the data time is too strong, then you still see backfolding artifacts. And if you regularize too much, then you see a cartoonish image like this one here. And there's also always the next equation from the audience. How do you pick lambda? Yes, good question, but I think we're out of time. And also, our approach in learning the regularizer, of course, we also learn the lambda of the data term. So what we use here is, again, the variational network I've explained in more detail before for image denoising. Our initial guess is now just a zero-field initialization, so we replace the missing information in the Fourier domain with zeros. This is our initial guess. Then we do some steps in the variational network, and then we hope that the reconstruction looks nice. So the variational network, as I've explained before, consists of T gradient descent steps of our energy. It's exactly the same energy, but now this linear operator A is now this combination of sensitivities and Fourier transform in the K-space. And when we look more closely to one step here, what we see here is, yes, exactly, it's the same as before. We are convolving with learned filters, applying some nonlinearity. We also will learn transpose filter here, sum together, and here is the force from the data term. And yes, I've already explained before, this can be, of course, seen as a certain convolutional neural network. So in order to find the best filter kernels and nonlinear functions, we do exactly the same bilevel optimization approach as before. So here we have a similarity measure. In our case, it was the mean squared error, which compares the current reconstruction with the reference. Our model has a lot of parameters, 100,000 in this case. And the similarity measure gives us some reconstruction error, which is the difference between those two images, for example. And this error is then backpropagated via computing the gradient to the variation network, and the parameters are adapted such that this image becomes more wide, which means that the loss function decreases. So in our experimental setup, this is not so easy. It's not so straightforward as for image denoising, but we are happy that basically we get fully sampled data, which takes a lot of time and costs a lot of money. And we can then just subsample by hand the data and try to reconstruct with the subsample data images with best quality, and can compare it with the reconstruction from the fully sampled data. So for training, we have 6 patients. That gives us 190 slices, and for testing, we also have 6 patients. Gradient descent steps is a little bit larger than in the case of denoising. We use 20 steps. We have 48 filter kernels per step, and the filter kernels are also a bit larger, 11 times 11. So altogether, it's 106,000 parameters we need to learn. So let's have a look at some learned filters. This is from the stage number 8. They look very similar to what we've seen for image denoising, but what we can also see is some specialized filters. They seem to avoid the backfolding artifact. So there are some particular filters that give a very high response if there are some backfolding artifacts, and these backfolding artifacts are then reduced since we have learned those filters. And the potential functions also look very similar, a bit more noisy. Maybe it's a problem that we still don't have enough training data, but basically we see more or less the same functions. So this is something very interesting. We are still not know how to interpret exactly. What you see here is now, this is the input, and this is the result after the first step for the learned model. So when I proceed here, it's sometimes very strange. The model starts to introduce certain frequencies. For example, from step 8 to 6 to 7, these things are introduced, so it looks much worse. Here the same. For example, here some edges are completely overemphasized, so the contrast has been much more improved, and some steps to the same. And then there are additional steps. For example, this was a step that does some smoothing. But it turns out that the intermediate image acts like a memory. So for example, you overemphasize certain edges, and then they are stored in this image because they are used later and they are regularized away later, or they steer the reconstruction for later stages. So it's a bit like memory that is used in deep learning currently, which is actually a very old idea, as we all know. But it has a similar effect to memory. So you can add certain information to the intermediate result, and later on this information is used or destroyed again, but it's very hard to interpret. So therefore, I'm saying the overall functionality is still a mystery, and we need much more to investigate this, of course. So this is the final result. Okay, some results. This is acceleration 4. This is the reconstruction with the least square solution with sense, backfolding artifacts for this type of contrast, and a lot of noise for this type of contrast. So there are different MRI images where you have different protocols that give you different contrasts, basically. This is the result with total generalized variation. So it looks better, but you see these backfolding artifacts are still in the solution, and it also looks a bit cartoonish. And this is the result with our learned network. So when you compare this, you see you get really a new quality of reconstruction. And the reconstruction time on a recent graphics card is 300 milliseconds per slice. This is another example now with acceleration 6, so only every 6th line the case space is taking sense, total generalized variation, and the reconstruction with our approach. Okay, so that brings me to the conclusion. So I was talking about learning better models for image processing. I have much more applications to JPEG deblocking, ink painting, but I simply didn't have enough time to talk about all of them. What we basically did is we applied empirical risk minimization using a loss function in order to learn the parameters of the models. And I was talking about 3 models. The first one, the very simple convex L1 model. Then the non-convex model based on the fields of experts prior. And finally, the most general model, which was the variational network. And our recent application is to compressed sensing MRI reconstruction. And our current challenge, what we're thinking about is, it would be very interesting to derive theoretical guarantees. So what's the sensitivity of the reconstruction? So we learn it for a certain amount of data, but what happens if we previously unseen data? So can we give some performance bounds on how good the reconstruction will be? Thank you very much.
Thank you. So, questions?
So I have 2 questions. The first one is not how to pick number, but how do you pick the size of the filters? It's like it's always a question, we use like 5 times 5, 7, 7 or whatever.
It's simply the larger the better, because if it's very large, the model can pick a smaller kernel by just setting everything around to 0. So it's basically a computational question. If you want to have an efficient model, then pick a smaller kernel, and if you can spend more time with your model, then take a larger kernel. For example, going back to the MRI, you basically see that here, for example, a large part of the kernel is not used. So gray means 0 coefficients, so they are not used, basically. So the model can decide by itself if the filter kernel was too large.
And the second question is, you said that this is like a convolutional neural network.
Yes.
So can you did you try to solve the same problem with a convolutional neural network? Because the question is actually, again, the filters. In the CNN, you can have layers of
yes.
filters. So you have in the first layer, you usually have things like edge detection. In
yes.
the second layer, you have the higher order.
Actually, we are exactly working on this type of idea. So, which relates to the so-called infimal convolution models I have shown before. So where you have your image, but you have additional layers of, and you where you can store additional information, and then you basically have 3D convolutions for this whole stack. Yes. We did not try to use an off-the-shelf model. I think it's not so easy. So here we really use the prior knowledge of the data term, of this Fourier transform. Then maybe you would need to train a fully connected, huge network, and I don't think that this is really so easy.
Yeah.
Another question is, so the applications really seem unlimited. As you said, you also have lots of examples. And my question would be, are there any problems where still handcrafted, well-defined models perform better? Are there any domains where you think the learning the models will not work as good as the denoising, for instance?
I mean, what we did is we did the simple way. We took a handcrafted model, just added a few more parameters and learned them. So per definition, it can only be better. The worst that can happen is that the parameters are all 1 or 0, and you don't need the additional degrees of freedom, basically.
Okay, so no limitations.
I don't think there's a limitation. So, I mean, the worst that can happen, you initialize with your handcrafted model, and it stays where it is. It doesn't improve. But normally it should improve.
Oh, that's usually people have limitation slides. Yeah, so it's very cool.
I mean, there are limitations, of course, but not in terms of the model, I think.
My question would be related to the MRI reconstruction.
Mm-hmm.
Do you think that you can learn more specialized models for particular types of MRI scans? So when you look at particular scans in particular body parts, or you might have more soft tissue, more bone structure, and if you focus on only these type of reconstructions, that you can find better, you can learn better models, rather than learning a model that tries to reconstruct all sorts of MRIs.
Mm-hmm. Actually, what you say is what we did. We learned, for example, for these 2 different contrasts, 2 different models. So actually, this is something you should do. For example, here you have different contrasts. We learned 1 model for this and 1 model for this. So you're right that when you have a specific domain or a specific type of images, specific contrast, then it is of course better to learn a specific model for this type of images here. Yeah.
We have the ground truth data for these images.
Yes, not in the slides. Unfortunately.
It's hard to imagine how much.
I can show it to you afterwards. I mean, you see it from the PSNR. If you're familiar with PSNR, if you're around 35, it's hard to see with your eye. It's a little bit what you're losing here, basically.
Any more questions from your side? Yeah, can you say something about the training data for different applications? How large are the training sets? And in particular for this kind of application, you said you had like 190 scans or so?
Yes, 190 slides. This sounds not much, but since we are learning convolution filters, you can basically think of that each pixel is 1 training example. Because when you apply a convolution, you apply it in a sliding window fashion. So each shifted patch basically is 1 training example.
And the slices are 256 square?
Yes, that's the usual resolution you have in MRI scans, yes.
Okay.
So around a few hundred images usually are enough. So we have tested with 200, 400 for image denoising, it doesn't make much difference.
And one more question, you said that you get the fully sampled data and simply take out the lines
yes.
in the spectrum. Is that the same as measuring it with real sampling?
I'm not an expert here, but according to our collaborators, yes. Maybe it's not 100% the same, but at least it's very similar, yes.
Okay. If you don't have any more questions, then thank you very much again.
Thank you very much.